So in this lesson, we'll be talking about Pollard's factorization method called p-1. So Pollard's p-1 factorization, in which a certain property of smoothness of numbers comes unexpectedly into play in helping factorizations that would otherwise perhaps be very difficult. And this is Dr. Eduardo Dueñez from UT San Antonio. So why try to factor numbers? Of course, part of the motivation is to try to break the RSA crypto system. Factoring numbers is not easy. So what if you had the large integer n, which is a product, let's say, of two primes, or just a product of large primes. If it has small factors, of course, you can sort of find those factors just by a brute force search, and you can factor them. But at the end, you end up with a large integer that maybe just what is known as very rough. Your integer n could be very rough, meaning that every single prime that divides it is very large. And doing so is far from trivial, and that's the whole point of finding methods that can work that are otherwise far from obvious. So now let's start with the concept of smooth numbers. So an integer, let's, take k to be an upper bound, let's say in the size of billions or maybe trillions or a little bit more. It has to do with how powerful your computers are, say. But the concept of k smoothness, for instance, 10 to the 9 smooth or 10 to the 12 smooth, means that an integer is a product of primes less than or equal than this particular integer k. So an integer is million smooth if it is a product of primes not exceeding a million, and so on. So that's the concept of k smoothness. And as I said, this has to do with uh, if you did things exhaustively by running, let's say, over numbers up to a million, billion, trillion. Like, when does your computer get really tired and start taking a really long time to run? Maybe after millions, billions, sorry, or trillions. More likely not beyond. So a smooth integer is k smooth if it is a product of primes not exceeding some k. And informally, you can just call an integer smooth if there's an understanding that its factors are not incredibly large. Now, this is the key to Pollard's p-1 algorithm. Yes, unsurprisingly, it is going to be based on Fermat's little theorem, which, for reference, for the nth time, Fermat's little theorem says that if p is a prime that does not divide an integer a, then p divides a's raised to the power p-1 minus 1. Now, the key here is that even though p is a prime, somehow the quantity p-1 plays a critical role in Fermat's little theorem. So of course, p could be a gigantic prime, but once you subtract 1 from p, p-1, if p is a large prime, p-1 is certainly going to be even. So p-1 is no longer a prime. And if you are very lucky, it could happen that p-1 is actually a pretty smooth number. And if that is the case, so let's just say that this p-1, right, the exponent p-1 is k smooth, right? So maybe k is, I don't know, a million or a billion. So all of its prime factors do not exceed this value of k. Now, if all of these prime factors were different, this is a really cool idea. Consider the number k factorial. So if all of the prime factors of p-1 were different, then certainly they would be prime factors of k factorial, right? Because each of them would be one of the factors of k factorial, which is actually the product of all of these numbers, 2 through k. So all of those primes dividing p minus 1, if they were all different, they would all be factors of k factorial, and therefore p minus 1 would divide k factorial. And in fact, even if there are repeated primes, if those repeated primes are relatively few and occur mostly in this mostly only small primes are repeated and not repeated too much, then there's still an excellent chance that p minus 1 will divide k factorial. So this is a pivotal idea that I'm going to refine more in a second, but this is the pivotal idea on which Pollard's p minus 1 algorithm hinges. Now, it may not literally happen that p minus 1 divides k factorial if p minus 1 is k smooth. But in all likelihood, it's going to divide a small multiple of k. So think of here, maybe it doesn't divide k factorial, but it divides 2 times k quantity factorial, or the factorial of 3k, or some really small multiple of k. In fact, it's easy to show that the absolute worst that could happen is that you take a multiple of k which is roughly of size, comparable in magnitude to logarithm of k. So a not very large multiple of k ensures that its factorial is divided by p minus 1 as soon as p minus 1 is k smooth. Right? And now the idea behind Pollard's p minus 1 method, right? So assume that n is a product of large primes. It's a really rough number. But perhaps you get lucky and some prime dividing n has the property that p minus 1 just so happens to be fairly smooth. Then you are going to be able to take a to the k factorial minus 1 and for a relatively small k, you're going to find that a to the k factorial minus 1 is likely, it is going to be divisible, as I said, by p, correct? Like, so this k could be the k of the smoothness here, or maybe 2k or 3k, whatever. So, but some relatively small the factorial of a relatively small number. And the base a doesn't really matter very much. You could take it at random. You could start by taking it equal to 2. And because of the smoothness properties of p minus 1, you wouldn't have to take too large a factorial to ensure that this k factorial is divisible by p minus 1. So immediately by Fermat's little theorem, you would get that a to the k factorial minus 1 is also divisible by p, which is great. And in all likelihood, it is only going to be divisible by p, since p got very lucky in that p minus 1 is fairly smooth. But in all likelihood, right, other primes are not going to be as smooth. Or you could just do it so that p minus 1 is the smoothest of them, say, if you want to think about it that way. Not that you would know this a priori, because you do not know the factors of n. But in all likelihood, as soon if you manage to have this be divisible by some prime p that divides n, right, then it is likely to only be divisible by p and by no other prime dividing n. But that means that by taking the greatest common divisor between this quantity and n, you have found a non-trivial factor of n, either p or maybe some power of p or something else. But in all likelihood, as soon as this shares a factor with n, the GCD is going to be, strictly between 1 and n, and therefore you will have managed to factor n. So with that in mind, let me explain finally what the Pollard p minus 1 method is. It's really an algorithm. The starting point of the algorithm is an integer n that is rough. This method is designed to try to start breaking a rough number into its factors. you should not try this method with an integer n that has small prime factors. You can always try and find those um, by any method, even by brute force, right? So after you get tired of doing brute force on n, you are left with an n that is pretty rough, and that's the input to the method, right? The output of the method is either a proper factor of n or the message failure if the method fails to find a factor. Um, and so the method, this algorithm is actually randomized in that, well, the integer a that we're going to use as the base and you know, to raise to powers, we can do that at random, whatever. Let's just say that it's a random integer between 1 and n. It's a residue class modulo n, non-trivial, you know, an interesting non-1, non-trivial, non-zero residue class modulo n. If you get extraordinarily lucky, it's not likely, right? But if for some reason you already happen to find an a that shares a factor with n, so this a is divisible by some extraordinarily large prime that it shares with n. So if that GCD is greater than 1, then you output D and you stop the algorithm because that D, which is the GCD of A and N, is greater than 1, right? If you get so lucky as for it to be greater than 1, you have found a non-trivial factor of n. Of course, remember that A is assumed here less than n, so this would be strictly between 1 and n. But this is really never likely to happen, at least if you're doing things right and your n is really rough. Otherwise, now let's really start with the nuts and bolts of the algorithm. Okay, so what we're gonna do is this little n is gonna be how many times, this is the factorial, and we're gonna go all the way up to n factorial as an exponent. And this is before giving up. There's no guarantee that we're gonna be able to find something interesting. As I said, the algorithm can always end up in failure, but you fix this number n. Just the running time is proportional to n, so keep this in mind. In other words, your n could be millions, maybe billions, but probably not more, unless your computer is a lot better than mine. So now what we're gonna do is finding the powers a to the something factorial, 2 factorial, 3 factorial, all the way up to little n factorial. Think about it that way. So what we're gonna do is the first thing, right, is start by every exponent 2, 3 up to a. The first step is we raise a to the power of j. So the first time this runs, a is gonna be a squared of the original a. The second time is going to be a to the 3 factorial, 4 factorial, etc., because each time you're raising to the next exponent, right? So anyway, at this point of the iteration, you should think of this current value of a being equal to a raised to the exponent of j factorial with the integer a that you had actually started with. So this a here is actually the original a, j to the power of j factorial. So here you're seeing if there is a common factor between a to the j factorial minus 1 and n. If that GCD, which is a common factor, the largest common factor, is strictly between 1 and n, then you have managed to find a non-common factor of d, right? Since d is a factor of n. So you output that d and you stop with success. Otherwise, you go back to the next value of j, 2 factorial, 3 factorial, etc., up to little n factorial. And if the loop ends and you never succeeded with some output, then after the end of the loop, you output failure and you stop, meaning that this trial failed either because a wasn't good, the random integer a wasn't good, or because maybe your largest factorial that you took in the exponent was just not big enough to capture the smoothness of p minus 1 for a factor p of n. So that's pretty much it. This exactly captures the prior discussion. So as a consequence to the existence of p minus 1, a Pollard's p minus 1 algorithm, we have something really surprising that if, let's say that you have an RSA parameter, a number capital N that is the product of two huge primes, an incredibly rough number, a priori really hard to factor. But if p minus 1, let's say one of the factors p has a property that p minus 1 is smooth, then you can use Pollard's p minus 1 method and you have and try to factor n. So you are likely to be able to use Pollard's p minus 1 method to find the factor p of n. So then n is a vulnerable RSA parameter. So there's really a deep moral to the story, which is that so the fact that you have a product of two very large primes that, and you think it is hard to factor, it's not necessarily so. You can try to use any method conceivable to try to factor n, and perhaps it's a method that you hadn't thought existed, but it does, right? So if you don't check the factors p and q so that p minus 1 and q minus 1 is still relatively rough, then you could easily break RSA, and this is not obvious. So a moral to this story is that your adversary is always going to use the best methods available to him or her, not, you cannot lull yourself into a false sense of security. But anyway, let's do a specific example of how the Pollard's method will work. I'm just going to take n, the product of two primes p and q, 7919 and 7927, whatever. Notice, so if I factor p minus 1 and q minus 1, p minus 1 turns out to be pretty smooth, right? We're looking at primes here of the order, several thousand, basically 10 to the 4. But p minus 1 has factors basically of size 100, 10 squared and below. So that is really rather smooth, all things considered. By contrast, q minus 1 is still pretty rough. The largest factor of q minus 1 is 1300. But because of this, you probably can guess that a trial of Pollard's p minus 1 method, as long as we get to the exponent 107 factorial, we're going to be likely to find a factor. So I'm just going to take the base 2, and I'm going to take the 2 to the 2 factorial, 3 factorial, 4 factorial, etc., minus 1 modulo n, right? And this is the list, and so on. And each of these is coprime to n, right? So this number's 3 is coprime to n, 63 is coprime to n, blah, blah, blah is coprime to n. And then we get to 2 to the 106 factorial minus 1, which is still coprime to n, but voila, exactly as you would have expected. Once you do 2 raised to the power of 107 factorial minus 1, 107 factorial is divisible by p minus 1. That's pretty obvious, right? This is actually a product of 3 primes, different ones, each of them less than or equal than 107. So when you get to 107 factorial, 2 to the 107 factorial minus 1 does share a common factor with n, and that common factor is exactly p, as you would expect. So again, everything works as promised.